Alo, các em nghe thầy nói không? Alo, Tùng ơi, nghe thầy nói không Tùng? Hôm nay em sẽ điểm danh cho thầy ha, điểm danh về ngẫu nhiên. Khi nào thầy khi điểm danh thì điểm danh ha, danh sách gửi rồi đó. Ha. Để không có điểm danh là tụi nó sẽ nghỉ học nhiều lắm, cho nên là điểm danh ngẫu nhiên khi nào thì cho ra chơi thì bắt đầu là điểm danh. Okay, so from good morning. I hope you have a good starting of this week. So this week we have many class of linear algebra, also of physics, because now um, the end of November, so that means you just have December and January next year to finish two courses, physics one and linear algebra. Okay, so some week we study a lot, maybe two classes or three classes. Okay, and I'm sorry about the recording last week because we have some problem with data storage. So TA cannot upload the recording, okay, into the YouTube channel. Okay, so I hope everything is smooth. Okay, this week. Okay, so today we finish lecture one, and then lecture one part one, and then we continue with lecture one part two. I already uploaded some lectures into the VGU model. Okay, so you can log in the VGU model and download some lectures of this course. So for TA, please make recording. Okay. Uh, so um, I hope all of you can see my screen. So again, if you have any questions, you can interrupt me and ask me. Okay, or you can type some questions into this message chat. Okay, and I can see your questions and I will answer to you later. Okay, so we review the knowledge last week. Okay, so last week we discussed about complex number, right? So that means if we have z, sometimes we use z over bar or z under bar or z over dot. Okay, so this is the symbols of a complex number. Okay, so this one equal to a plus jb. Okay, we use j because we will avoid the confusion, right? With current I. Okay. So we have five representation of complex number. This is number one. Number two, we have z a absolute value of z with 5. Okay, so that means we need to calculate absolute value of z. That's a uh, equal to the square root of a square plus b square. We have tan phi. Okay, and then you can get a phi. This is phase angle E tan to the power of minus 1 b over a. Okay, yes, of course it depends on different quadrant. Okay, we have fourth quadrant, second quadrant, third quadrant, and fourth quadrant. Okay. Sorry, so we have number three. So we have z a z e to the power of j phi. Okay, so number four, we have z a absolute value of z cosine phi plus j psi sorry plus j psi phi. Okay, and we have number five, we have z a absolute value of z. Okay, e to the power of j phi. Okay, plus e to the power of minus j phi over 2 plus j e to the power of j phi minus e to the power of minus j phi over 2j. Okay, so that means you can yeah, you can delete this one. Okay, so and then this one equal to z e to the power of j phi. Okay, this is the content we already discussed last week, right? And now yeah, we also yeah, last week we also discussed about I, this current equal to Im cosine omega t, okay, plus theta. Okay, so if we have the general format of current like this, so we have three cases, right? We have case one. That means theta is 0. So we can get Im cosine omega t. So K2, that means theta is positive. Okay, so you can get Im cosine omega t plus theta. What does this mean Im? Im mean magnitude of the current. Okay, yeah. And because this one is capital Im, so this is the constant. Okay, Im is constant, and here we have lowercase. Okay, lowercase I, so this is instantaneous current. Yeah. So K3, K3. So if theta is negative, okay, so to get this general formula, I should be Im cosine omega t minus theta. Okay, because this is negative, so minus of minus, right? This is negative, so minus of minus, you get positive. Okay, so totally we have three cases. Okay, and then you can draw the waveform, right? Okay, so remember that for case one, okay, so you get the waveform like this. Okay, this is omega t, this one is here I1, here I2, here I3, so this is I1. Okay, so omega t is 0, you get big. Okay, and this one is 90 degree, 180 degree, 270 degree, and this is 360 degree. Okay, this is minus 90, this is minus 180, this one is minus 270, and this one is minus 360, because here at the left side this is minus infinite, this one is positive infinite. Okay, so this is 0, right? So at the right side, all values of omega t should be positive and vice versa. Okay, all values at the left side will be negative. Okay, so this if omega t is 90 degree, you get 0, 0. Okay, and then big, then big, then 0. Okay, and then big. Okay, so we can draw the waveform like this. Okay, yes, yeah. Okay, so this is I1, right? So now we come to I2. So if omega t, and we assume, so we assume theta is 90 degree. Okay, we assume theta 90 degree. So this one is plus 90 degree. This one is minus 90 degree. Okay, so this is plus 90 degree. So if omega t is 0, cosine 90 degree is 0. Okay, and if omega t is 90 degree, okay, 90 degree, so 90 and 90, you get 100, 180, so you get big negative. Okay, so now a big positive, 0. Okay, so you get this one. Okay, so this one is I2. That means left shift, because the left. So now minus theta. Okay, minus theta. This is negative. So the no, this one right. Okay, so if the t uh, 0 gets cosine minus, so 0, and if t is 90 minus, you get 0. Okay, so big here. Okay, so this is 0, this is big, and you get the waveform like this. Okay, so this is I3. So remember that when we show I1 here, right, and so here I3, I1 and I3. So okay, but this one is plus 90. This is the main knowledge of last week. Now we similarly we consider I am sine omega t. Okay, sine omega t plus theta. Okay, because this is sine, so yeah, we have also three cases, I1, I2, and I3, right? This one is I am sine omega t plus 0. Okay, this one is I am sine omega t minus theta, and this one is I am sine omega t minus theta. And of course this one is left shift, because this is plus the theta and this is minus theta. This one is right shift. Okay, but remember this one is sine. Okay, sine. Yeah. So you can draw the waveform, right? You can draw the waveform. Okay. So now we have the waveform. Remember that because this is sine. Okay, so if omega t is 0 and theta is 0, you get I a 0. I 0. So that is the reason if we have cosine, we consider the big value as the y-axis. Okay, but if we have sine, we consider this 0. Okay, so now I turn the waveform. So we consider this one. If this is omega t, this one is I1. Omega t is 0, you get 0, right? Yeah, you get 0. Okay, and this is 90 degree, 180 degree, 270 degree, and 360 degree. Minus 90, minus 180, minus 270, and minus 360. Okay, so if omega t is 90 degree, okay, you get big. Okay, 0, you get big. Okay, yeah. So yeah, if minus 90 degree, you get a negative big. Okay, so you get a waveform like this. Do you agree with me? Okay. Yeah, you get a waveform like this. Yes. Okay. So that means at the origins, okay, yeah, you consider 0. You consider 0. Okay, this is different with cosine. If cosine at the y-axis, we consider big, but now we consider 0. Okay, and now we have I2. Okay, so look, we have I am sine omega, and we assume theta is 90 degree. Here you get plus 90 minus 90. So if omega t is 0 degree, okay, 0 plus 90, you get big, right? You get big. Okay, and if you get big, okay, and if omega t is 90 plus 90, so you get a negative, you get 0, and this one you get a negative. Okay, like this. So you get I1, I2 here. Yes. So if we consider the phase angle, look, okay, here we consider this 0 and this 0. Okay, so we have phase shift 90 degree plus 90 degree. Okay, and then we have this one is I2. Okay, now I3. Okay, I3 here. If omega t is 0, 0 minus 90, so you get minus 90. Okay, so you get a negative, right? You get a negative peak. Okay, then positive, negative, 0, positive. Okay, like this. Okay. Yes, this is I3. And if we compare this 0 point and this 0 point, so we also get 90 degree. Okay, but this one is right shift. This one is here, left shift. Okay, yeah. And now if we apply this complex number, okay, so here we have IM, so I indicate IM, I1, E, IM, right? This is magnitude with the phase angle 0. I2, EIM with the phase angle plus 90. And I3, EIM with the phase angle minus 90. Okay, we could, yeah, they are in the same of side. Okay, side function. Okay, so if we draw the polar form, this is polar form, right? Yeah, here. Okay, this is x-axis. This one is y-axis. Okay, so we have I1 will be here, right? I1, because I1 is IM with 0 degree. Okay, of course, this magnitude, okay, this absolute is IM, right? And we have I2. I2 is, because this is left shift, so I2 is leading to I1, so this is I2. Okay, and of course the magnitude is IM. Okay, so this is the circle, right? So we have the circle, yeah, we have the circle with the radius of IM, right? The radius of IM. Okay, and now we have I3 like this. This is I3. Okay, yeah, and of course we know the phase angle here is theta. This is minus theta. Okay, so I demonstrate to you we can convert the waveforms, right? The waveform into the polar form, into the polar form with complex numbers. Okay, yeah. So we finish for review, right? So we have case A, we are considering IM cosine omega t and plus theta, and case B, okay, I is IM sine omega t plus theta. So we have the observation. So it's up to you. We can use cosine waveform or sine waveform. Okay, that's okay, because they have the same meaning. We have totally 3 cases. Case 1, case 2, case 3. Case 1, that means we consider the bigger value if we have cosine, and we consider 0 if we have sine function. And I2 left shift with some phase angle, some theta, and I3 right shift. Okay, waveform. Any questions? Okay, let me check. Okay, no questions. I don't understand the first one. Okay, so the first one I already explained to you last week. Okay, so and now I just review. Okay, so if you don't understand, you also don't understand. Just STA. Okay. Okay, so that is the reasons you should attend my class. You should review the lecture at home. You should watch the recordings if you also don't understand. And of course, we already have TAs. They will help you. Okay, I emphasize many times. You should use the 30 minutes when I finish the lecture. Okay, to HTA. Okay. So now we come back the lectures. So we know from V is the voltage and I is the current. Okay. So if you take the B is V times I, you get the power. But to be careful, because I write here V, I, B, all of them are lowercase letter. Okay, lowercase. That means I is the function of times, V is the function of time, and B is the function of times. Okay, yeah, we discussed before, right? Look, look, lowercase letters for time varying voltage or current. That means they are the function of times. Okay, for example, here it is lowercase I. So I is I am cosine omega t plus theta. Okay, so this is the function of time. Look, t. Okay, so if I write here V or I, that means I mentioned they are in the function of time. Okay, yeah. So the function of time is what? The function of time that means VE, VM, right? Maybe cosine omega t plus theta V. Okay, theta V, this is the phase angle of voltage. And IE, I is what? IE, IM, right? IE, IM cosine omega t plus theta I. Okay, and B. Okay, how can you get a B? So we can calculate BEV times I. Okay, BEV times I, that means EVM cosine omega t plus theta V times IM cosine omega t plus theta I. Okay, theta VE, the phase angle of the voltage, and theta I is the phase angle of the current. Or you can calculate the instantaneous power by these formulas. Yeah, BE I square times R. What does this mean, R? What's a R? RE resistor. RE resistor. Okay. Okay. Yeah. Or you get the BEIM, right? Time R cosine omega t plus theta I. So this is the instantaneous power dissipated by the resistor. Okay, now we would like to calculate the average values of power. Okay, so when we calculate the average, we use capital, right? We use capital B. Why? Because average values is the constant. Is the constant. So we have B, this is capital. B average E I square totally average. Okay, time R. And we divide I square totally average E I effect square, effective values. Okay, so that's mean, okay, so now we have I effect square E I square totally average. So if I take the square root of both sides, okay, so the square root of I effect square E I effect, and this is the square root of I square totally average. That means we take I square first and then we take average later. Okay, so remember that's I square average, different I average, totally square, very different. Because for this one we take square first, average later. Now we take average first, square later. Okay, so they are different. They are different. Remember that. So now we define I effect, effective current E RMS. What does this mean, RMS? You study at the high school. Root, right? Mean square, right? Vietnamese mean is giá trị hiệu dụng. Okay. So now we know how to calculate RMS. RMS root means square value. This is the square root of I square totally average. Okay, yeah, root mean square. So now, or you can calculate root mean square values by these formulas. Of course, you know this formula at the high school. Yeah, for sure. Okay, so IRMS. Okay, this is the constant. So we use capital. Remember, if we have the constant value, we use capital. If this is a function of time, we use lowercase letter. Okay, small letter. Okay, E 1 over t integration from 0 to t I square t dt, and then we take average. Like this. Okay, sorry, we take the square root. Okay, so we have the square root of 1 over t, the integration from 0 to t I square t dt. Okay, you can guess IRMS. So we have two ways. To calculate IRMS. Okay, by using these formulas or this formula. Okay, now we have example. The question is how to find the RMS values, which means where values of a square wave current that jump back and forth from 0 to 2 ampere. Here, this is I. Okay, so if we remember the formulas, we have I RMS E the square root of 1 over t 0 to t I square t dt, or IRMS E the square root of I square average, right? Average. So now you get I, right? Okay, this is the waveform. This is the square wave of current. Okay, so we take I square. Okay, we take I square first. You get this is 0, 2 square, you get 4. Okay, so you get the form like this. Okay, and of course this one is 0 and this one is 4, 4, 0. Okay, and then you can take average. Okay, we take average, you get 2, right? You get the 2. So now we have IRMS E square root of 2. The square root of 2. I am sorry, it's wrong because when we take the average, you get oh yeah, we have here this is the square root of I square is 4 for average, right? For average, or I just okay, let me explain. Okay, so here this is 0, this is t. Okay, one period, next period. Okay, this is period, next period, and so on. Okay, so for one period you get this area. Okay, this is t over 2, right? Because this is this is one period, so here is t over 2, this is t over 2. Okay, so we have 4 times t over 2 plus 0 times t over 2. Okay, divided by t. Yeah, you get the average of one period. So this is this one, so you get a 4, you get average, right? I square average. Actually t and t. Okay, you get 4 over 2, you get 2. So here you get a 2. Okay, so IRMS is the square root of 2 amperes. Okay, yeah. Any questions? Okay, so Now we consider the voltage. Okay, I mentioned to you before, we have this general representation of the voltage. Okay, V is Vm cosine omega t plus theta v. So if theta v is 0 for simplicity, okay, yeah, for simplicity, normally we assume that theta v is 0. So you can get V is Vm cosine omega t. Okay, so you need to calculate the average. Okay, this is VRMS. We calculate root mean square values of the voltage. So that's E, the square root of V square average. Okay, so now we need to make clear, okay, what is Vm? So Vm is magnitude value, and VRMS is root mean square value. Okay, they are on constant. Why we know? Because this is capital. Okay, they are on constant. So this is the waveform of cosine omega t. Okay, yeah, V cosine omega t. So now you get we take V square. So V square average, and V is here. Okay, so you can get Vm square cosine omega t square, totally take average. Okay, so Vm, so here you can get what? The square root of Vm square, right? Vm square, and then the square root of cosine square omega t take average. Okay, so the square root of Vm square is Vm. Now we focus on cosine square omega t average. Okay, so this is cosine omega t. This one is cosine square omega t. Then when we take average, you get 1 over 2. Okay, so now you can get VRMS E Vm, the square root of 1 over 2. That means you can get Vm over the square root of 2. Okay, yeah. So I demonstrate to you. Okay, yeah. At the high school, normally when we calculate VRMS, this is magnitude over square root of 2. And now you know why, right? Right. Because we apply these formulas. This formula we discussed before, right? So now we know any RMS values will be equal to the ratio of Vm to square root of 2. Okay, please remember that VRMS is Vm over square root of 2, or you can know VME VRMS times square root of 2. Okay, yeah. Any questions? Let me check. Does IRMS means that the circuits consume power equivalent to that of the circuits with a DC current equal to IRMS? Let me think. Let me answer to you very briefly, because you study another course, electric circuit, you will understand more. Okay, so now the answer is A, no. Okay, why? You know, now we are studying the linear algebra, not physics 2, not the linear and not electric circuit, but I just give you very brief explanation. Okay, so now we should make sure you understand what is a DC signal and what is AC signal. Okay, Yeah, you should understand. Okay, so if you've confused the true meaning of DC signal and AC signal, you cannot answer the question like this. Okay. Okay. So come back. So what is the DC signal? Okay. So the DC signal is the signal with the value to be positive or negative following the time. Okay. For example, this is the time, right? Following the time. This is minus infinite. This is positive infinite. So this is DC signal, right? I want DC signal because the values of I1 is always positive following the time, or I2. Okay, so the values of I2 is always negative, right? Negative because this is minus infinite, this is positive following the time. So this is DC signal. Okay, we have another case. So like this. What is this? This one is also DC signal. DC signal. Why? Because the values of I3 is always positive. But we have of course this is sinusoidal waveform. This is sinusoidal waveform. But it's a DC because the values is always positive. The values of I3 is always positive. Or we have this one also positive, right? So this one is also DC signal, not AC. Okay. Or we have the case like this. Like this. This one is also DC signal because the values of I4 is always negative. Okay. Yeah. Of course, I4 like the sinusoidal waveform, but the values of I4 is always negative. So this is DC signal. Is it clear? Now AC. AC signal means we have basically we have some positive, some negative, some positive, some negative following the time. For example, here. Okay, following the time. This is minus infinite, this is positive infinite. So we have the current IAC 1 like this. Right? Sometimes positive, sometimes negative, positive, negative, positive, negative, positive, negative. So we say AC signal, alternating current, because because on for these periods the current is positive, next one negative, next one positive. Okay, so this one we say AC, or we have the signal like this. Okay, so this one is AC signal. Okay, even though we have more positive and less negative, but this is AC because we have positive, negative, positive, negative, or we have the other one. Okay, we have AC signal like this. Times, yes. Okay, this I will say harmonic. We study it later for another oscillator circuit. So this is more positive, this is negative, positive, negative. Okay, so this one we say AC because the value of current will be changed from positive to negative and vice versa. Okay, so now I hope you understand fully what is the meaning of DC signal, what is the meaning of AC signal. Of course, for practice, we have, if we have DC signal, the signal should be what? Constant. That means flat, okay, or negative, okay. We don't want to get some distortion or some uh, variation like this, okay. So if we would like to get AC, right, AC signal, we hope we get the signal like this if we follow the sine waveform, okay. We hope, okay, that means we get balance between positive and negative. Or if we have cosine waveform, you get the waveform like this, right? We hope we get okay, symmetric waveform. That means the positive areas of the positive equal to the areas of negative. Okay, we hope we get this waveform. Okay, this one we say balanced AC signal. Okay, yeah, because the positive areas will be equal to the negative of area. Okay, we hope. Okay, for ideal, okay, for ideal case, this is DC and this one is AC. Okay, now come back to the questions. So, so when we have IRMS, when okay, so we have IMS value if we have AC signal, we get IMS. Okay, so IMS values occurs if we are considering AC signal. AC signal. So we have IRMS is the square root of 1 over t 0 to t I square t dt, right? Or we have VRMS is the square root of 1 over t 0 to t v square t dt. Okay? Yeah. So for AC signal, we more focus on RMS value. Okay, so how about DC signal? DC signal, we focus on average values. So we have average current A1, 1 over T d square root, the integral from 0 to T, IT dt, right? Or average current A1 over T 0 to T Vt dt. Okay, now if we try to calculate average values for AC signal, you are stupid. Why? Because when we apply the formula to calculate AC signal, the DC, the average values will be zero. That's meaningless. Okay, so for AC signal, we seldom consider average value, because if you get balanced waveform, the average will be zero. Okay, average will be zero. So for AC signal, we focus on RMS value. For DC signal, we focus on average values. Okay, yeah, and of course, for DC signal, average value will be equal to the RMS value because this is constant. This is constant. Okay, so, yeah. So I give you very brief explanation about the DC current, RMS current, okay, average current, or average voltage, RMS voltage, IC voltage, okay. And then when you study more for physics 2 or electric circuits, okay, you can understand more. Okay, is it clear for you? Okay, so now if we have the circuits like this, okay, this is DC voltage, right? And this is current. This is a resistance. This is current IDC. Okay, this is V DC. So we have the power is I DC times R. Why I use capital? Because this is constant. Okay, so B E I D C, B D C E I D C times R. Okay, now if we have AC voltage, okay, and this is R, to be careful, you must use little v, little I. Why? Because um, this is this sinusoidal waveform, so we need to calculate V E I times R. This is instantaneous voltage, instantaneous current. B E V times I or I times R. So you can need to calculate B average, how many? Okay, yeah. Okay, so to be careful, for DC you can use capital, but for AC you should use little v, little I, because they are all the function of time. They are instantaneous. Okay, yeah. Okay, okay, good. Okay, I hope you can enjoy the discourse. Okay, so for coming back, example, look, find an instantaneous voltage for 120 volt 60 hertz voltage delivered to your home. Okay, so we know the frequency is 60 hertz. Okay, this is the value, right? This is the values. This is the constant. So the voltage here is RMS. Okay, 120 volt. Yeah, so you can calculate, you can indicate VE VM cosine omega t plus theta v, right? This is the general. This is the general. So we need to calculate VM. Okay, so VM is what? This is magnitude, right? So VME, this is square root of 2 times VRMS, because VRMS, right, is VM over square root of 2. That means the VM is VRMS times square root of 2. Yeah. Okay, so you can get the VM is 169.7 here. Okay, we need to calculate omega. So omega is 2 by F, and F is 60 hertz. So you can get 2 by 60 equal to 377 radians per second. Yeah, time t. And we assume theta v is 0. Okay, so you get it. Yeah, so we can get the general representation of instantaneous voltage. Okay, yeah, just a very simple example to help you understand what is RMS value, what is magnetic values, what is instantaneous. Okay, current and voltage, also power. Okay, now we apply the complex numbers into electric circuit, very simple electric circuit. Okay, what is this? This is resistance. Okay, yeah, as I mentioned before, because this is AC voltage. Okay, AC voltage. So to be careful, we need to use little v. Okay, so this is the function of AC voltage, right? VE the square root of 2 V cosine omega t. This is the current. This is resistance. Okay, so if we analyze this one, okay, so now we have V. What is V? So sometimes they use VRMS, okay, or to be simply to be simple, we skip RMS, we just write V. Okay, so you should remember if we write V, that means VRMS. Okay, IRMS, I just write I and I skip a script RMS. Okay, just for symbol, you know. So here is VRMS. The times square root of 2. So square root of 2 times V, this is VM, right? The VM. Okay, VM. Yeah, VM. So we know VE, VM cosine omega t, and VM is square root of 2 times VRMS. Okay, I mentioned before. Okay, sometimes we skip RMS, you just use V. You get square root of 2 times V times cosine omega t. Okay, or plus 0. Do you agree with me? Yeah. So we have to calculate the current. So the current, we apply Ohm law. So the current is voltage over R, and the voltage here is Vm, right? Cosine omega t over R. Okay. So Vm is the square root of 2 Vrms over R, and we skip Rms, you get the square root of 2V over R. Cosine omega t or plus 0, plus 0. Okay. Yeah, plus 0. Now, now I would like to indicate the complex number. Okay. Now, this is cosine. This is cosine. So they have the same waveform, right? The same format. Now, I can get V E, the square root of 2 times V. This is magnitude value, right? Magnitude value with the phase angle 0. And we have the current E, the square root of 2 times V equals divided by R with the phase angle 0 degree. Okay, so sometimes we use V like this, or we use V dot. Okay, this complex, right? Or vector V, okay, or V over bar, V under bar, okay, complex number, or we just say I over dot. Okay, so now, you know, this is 0, this is 0. So that is the reason at the high school we say if we have the lot, if we have the lot E, resistance, the voltage, and the current have the same phase, you know, the same phase. Why? Because here is 0, here is 0. So because phase angle of the resulting current is the same as the phase angle of the voltage. So if we have the resistive lot, okay, the voltage and current have the same phase, okay, have the same phase. Okay, so now I would like to indicate a waveform. Okay, so come back. We have I E square root of 2 V over R cosine omega t, right? Yeah, yeah. And VE, the square root of 2 times V cosine omega t. So now I draw the waveform. Okay, I draw the waveform. This is omega t. This is current. Okay, look, omega t. So if omega, maybe I draw the voltage first. Okay, voltage. So omega t. So if omega t is 0, you get 1, right? 1 times square root of 2 times V here. Maybe here is square root of 2 times V. Okay. And if omega t is 90 degree, cosine of 90 is 0, 0 sum this one, you get 0. Okay. So this is 90 degree minus 90 degree, 180 degree, 270 degree, 360 degree, 180 degree, minus 270 degree, and minus 360 degree. Okay, so you get the voltage like this. This is square root of 2 times V. So this is minus square root of 2 times V. Okay, get big, 0, negative big. Okay, so you get the waveform like this. Yes, do you agree with me? It is 0. Okay, so this is voltage, right? So if omega t is 180 degree, okay, so cosine of 180 degree is minus 1. Okay, so minus 1 times square root of 2 times V, you get minus square root of 2 times V here. Okay, so the current, come back to the current. This is cosine omega t, this is cosine omega t. So we have the same, the same phase, but for example, here is square root of 2 times V over R. This is minus square root of 2 times V over R. Okay, over R. So we have the same phase. Yeah, we have the same phase like this. Okay, the same phase. So if the voltage gets 0, the current gets 0. If the voltage gets negative peak, the current gets negative peak also, because they are in the same phase. Okay, so this is the waveform. So now I would like to indicate the polar form. The polar form, if the voltage like this is voltage. So the current like this. Vector, right? The current like this, because the voltage and current have the same phase. Okay, so if here we plus 45 degree, this one should be plus, okay, 45 degree. Okay, so the voltage, it is plus, so the voltage like this, 45 degree. Voltage here, and the current, the same phase, right? The current will be here. So yeah, to demonstrate to you, if we have the circuit like this, load E resisting, voltage and current have the same phase. Now we already applied the complex numbers into electrical engineering, into this circuit. Okay, this is clear for you. That is the reason, you discuss, because I know of linear algebra, I know electrical engineering. Okay, so we can apply the knowledge of linear algebra into electrical engineering field. Any questions, please? Okay. Okay, let me check. Maybe we have some questions. Okay, no questions. Any questions? So if I ask you, do you have any question? If you have question, okay, don't be shy. Just ask me. Okay. So now we can guess IRMS, right? IRMS is magnitude current over square root of 2. Okay, and magnitude current is what? Magnitude current is here. Okay, so square root of 2 times V over R divided by square root of 2. So you get V over R. Okay, or we can say RMS current is RMS voltage over R. Okay, now we need to calculate average power. I mentioned before, right? B is V times I. B is V times I. So if we have B average, if we take average, you get V times I totally average. Okay, yeah, and because average value is E, the constant, so we can say B, capital B average. So capital B average is V times I, and then take average. So V is E here, right? V is square root of 2V cosine omega t. Yeah, V. And this is current. Okay. Yeah, we take the product first and then take the average later. Okay. So it's square root of 2 and square root of 2, you get a 2. This is constant, so take outside. V and I, they are on constant, so you take outside. So that means we just take the average of, this is cosine omega t, cosine omega t. So you get cosine square omega t, we take average. And we know cosine square omega t average is 1 over 2. Yeah, we studied before, right? We have this example like this. Yeah, yeah. Cosine square t, we take average, you get 1 over 2. Okay, so here you get 1 over 2. Okay, so 2 and 2 delete. Okay, you get a V times I. So for the circuit like this, okay, we can get the average E, V times I, RMS voltage times RMS current. Okay, and we know I is V over R, so you get I square R, right? B average E V times I, and I E V over R, so you can get V square over R. Okay, or you know VE I times R, and then you times I, you get I square R. Okay, so now I demonstrate to you, if you understand complex numbers, you understand how to draw the waveforms. Okay, yeah, you can analyze any electric circuit. Okay, now we have another example. Okay, we have another example. We consider another circuit, but now this is capacitor. Okay, and the values of capacitor is capacitance. Okay, so we have the AC voltage and the waveform like this. Okay, VE the square root of 2V cosine omega t. It is current. Okay, and we know the formula, right? We know the formula. IEC dV over dt. Okay, yeah, at the high school, you know this formula. IEC dV over dt. Okay, so now we know V, right? V is square root of 2V cosine omega t. You need to calculate I. Okay, so IEC dV over dt is C. Okay, and VE is square root of 2V cosine omega t. Omega t. So derivative, right? So square root of 2 and V are constant. Take outside. Okay, see you right here. Okay, so cosine omega t derivative. Okay, yeah, derivative of cosine omega t with respect to time. So you get you get what? I think you remember, right? Cosine omega t derivative is minus sine omega t, and omega t derivative. So you get minus omega sine omega t, right? So here, minus omega sine omega t. Yeah, and we know minus sine omega t is cosine omega t plus pi over 2. Here, here. Here we have square root of 2 omega c v. That means minus sine omega t is cosine omega t plus pi over 2. Yeah, that's it, correct. We demonstrate. This is cosine. This is sine. So if omega t is 0, okay, yeah, so maybe 90. Okay, so omega t is 90, so sine 90 is 1 minus. That means you get here. right? Minus 1 here. Now, if omega t is 90 plus pi over 2 doesn't mean 90 because pi is 180 degrees. So you get cosine 180 degrees is minus 1. Okay, so the same. So minus sine omega t is cosine omega t plus pi over 2. So you get it what? Now, look. We have the comparison. So, V is square root of 2V cosine omega t plus 0, right here. Now, current is what? Square root of 2 times V, right? And then omega c, right? Cosine omega t plus 90 degree. Okay? Yeah. Of course, we have the same cosine but different phase angle. Now, if we use complex number, you get vector VE. E what is square root of 2V with the phase angle 0. Now, for the current you get square root of 2V omega c, right? With the phase angle how many? 90 degree. Okay, and you know, first of all, you need to make sure V and I the same format. This is cosine, this is cosine. Okay, so we can indicate the waveform into the complex number. You get square root of 2V with the phase angle 0. Square root of 2V omega c 90 degree. Okay, yeah. Now, if you draw the polar form, here is vector V, right? Here is vector V. Here is vector V. Right? Why? Because this is 0. And you stay here. Okay, we follow the counterclockwise, you get positive waveform. So V here. Because this is 0. How about the current? The current with 90 degrees, so the current will be here. The current will be here. That means the current is leading to the voltage 90 degrees. Okay, I demonstrate to you at the high school. You study if we have C. The current is leading to the voltage. That means dòng điện sớm pha hơn điện áp. Okay, the current is leading to the voltage. So look, okay, the current is said to be leading the voltage 90 degree. Okay, yeah, and you can draw the waveform. This is the waveform. Okay, this is the polar form, right? Yeah. So if the voltage is here, so the current should be here, you know, because we follow counterclockwise direction is positive waveform. Okay, if the voltage is here, current here, you know, so if the voltage here, the current will be here because we follow counterclockwise waveform. So the counterclockwise direction, okay, positive. Okay, yeah. And then we can know the current is leading to the voltage 90 degree. Okay. Any questions? So now we draw the waveform. Look. Remember, voltage is what? Here. Square root of 2 cosine omega t plus 0. The current E here, you know, square root of 2 V omega c cosine omega t plus 90 degree. Okay, 90 degrees. So You can see this is 0, this is 0, this is t, right? So you get the waveform like this. If omega t is 0 degree, you get the peak. Okay, 0, negative peak, blah blah. So this is the waveform of the voltage. Now for the current, and this is the same cosine, right? But here we have plus 90 degrees. Plus 90 degree mean what? Left shift, right? Left shift. So if we have 0, right, the peak will be here. But now we plot theta. So we left shift with 90 degree, okay? So if here is 0 and then you left shift 90 degree, you get here 90 degree, right? Minus pi over 2, okay? And the peak of the current will be here. The peak of the current will be here because the current will be left shifted 90 degree with the voltage. Okay, so if here the voltage is 0, so the current left shift with 90 degree. Okay, so if we have I is square root up to v omega c cosine, no, sorry. So maybe if we have the current, I just assume, if we have the current is Im cosine omega t minus 90 degree, minus, that means right shift. How many degree? 90 degree. Okay, so you get the waveform like this, now this is the peak. So right shift 90 degrees. So this is pi over 2, right? So you get the peak now here, okay? Because we make right shift with a 90 degree. Okay, so you get the waveform like this. Okay, yeah, and then here is get peak at pi over 2. Okay, so this is the waveform of the voltage and current, okay, for the circuit here. Okay, now, yeah, okay, and here I emphasize to you, okay, so because this is 0 plus 0, so the peak value will be at the y-axis. Now plus pi over 2, so left shift 90 degree. Okay, 90 degree. So now the peak of the current will be here, so you can get the waveform like this. Okay, and then similarly we can calculate the average power. Yeah, so now instantaneous power B is V times I. Okay, this is V, this is I. Okay, and after some modification, you can get instantaneous power is here. So when we take the average, power, you get 0. Why? Because now instantaneous power is the waveform of cosine like this. Oh, like this. Sorry. Okay, so I can indicate a waveform of the instantaneous power for you. Okay, so this one is 2 omega t, and this is plus pi over 2, so that means left shift. Okay, left shift pi over 2. Okay, so you get the you can get the average power like this. Okay, this one is 2 omega t. Yeah, 2 omega t. Yeah, so this is positive, this is negative. Okay, so when we take the average, of course, average power dissipated by the capacitors will be 0 because the positive area equal to the negative area, right? Yeah, so the average power dissipated by the capacitor is 0. Okay. Okay, so yeah, we have example for your reference. Okay, very easy, just very briefly. Okay, so we have look, this is the voltage, this is constant. This is constant, so we are MSE 120 volt, and the frequency is 60 hertz. Okay, this is the capacitance, 10 the microfarad. Okay, that means 10 times 10 to the power minus 6 farad. Okay, so just apply the formula, right? We have I E 0 up to V omega C cosine omega t plus theta. That's pi over 2. Okay, so theta is pi over 2. Okay, omega is 2 pi f. Okay, so this is 2 pi, f is 60, so you get 60 times t. Cosine here, the 0 up to here, so we need to calculate v WC, v omega c. So v omega c omega e 60, 2 by f. Okay, omega 2 by f, 2 by 60. C is what? 10 microfarad. That means 10 times 10 to the power of minus 6. Okay, and the voltage is 120. So you get the current here. Okay, so here. Yeah. So what is it? What is it? This is IRMS, right? Right. So here is IRMS. Do you agree with me? Yeah. So, and then you can get this one. So this is the instantaneous current for the circuit here, voltage. This one is capacitor. Okay, this is V, this is I. Okay. Yes. So look at this one. We have I a omega c times V. So I can write here I is V over ZC. That means 1 over ZC is omega c, right? Here. Or ZC is 1 over omega c. Look, this is omega c. So this is 1 over ZC. So that means I define 1 over ZC is omega c. That means ZC is 1 over omega c. So what is ZC? What is ZC? What is ZC? So ZC is capacitive impedance. Capacitive impedance. Vietnamese meaning tổng trợ, mang tính dùng. Okay. So at the high school, you calculate XC first. Okay. So XC is 1 over J omega C. Sorry. This one you should have. Sorry. Okay. You need to use J here. Okay, so XC is 1 over omega C. Okay, and we know ZC is minus J XC. That means minus J1 omega C. Okay, so if I time J here and I time J in the numerator. Okay, so J and J square, right? J square is minus 1 minus and minus, so you delete, so you get 1 over J omega C. Okay, so when we consider ZC is 1 over J omega C, and this is XC. Oh, XC is what? Reactance. Okay, capacity reactance. Yeah. Okay. So why we get minus here? because this is a voltage, okay, and this is current. So current E lead into the voltage. Okay, current E lead into the voltage. That means if the voltage we have 0 degree, the current should be plus 90 degree. Okay, now we look, we have I EV over ZC. Okay, so VE 0 degree, ZC. Okay, ZC is minus here. Okay, so that means ZC with minus 90 degree. So you can get V over ZC minus 90 degree. Okay, get the numerator. Okay, so you get what? You get plus. Sorry. You get plus 90 degree here. Okay. Yeah, so that's the reason we have the minus here. Okay, we have minus here because you would like to get a minus 90 here, and the current should be positive 90 degrees. Okay, so if we apply the complex number, right, this is 0, this is minus 90. So if you move to the okay, numerators, okay, so you get plus 90. So 0 plus 90, you get plus 90. Okay, yeah, so for the high school, yeah, we know, right, Z is minus JX. Okay, or ZCE 1 over J omega C, the same. Okay, any questions? Maybe we have some questions. Let me check. No questions? Okay. Then continue. Okay. So now let me check. Now we apply the complex number into idealized inductor. This is inductor, right? This is inductor. So we have the voltage. We have the current. Okay. We already know the voltage. We would like to figure out the current flow. The current flows through the inductor. Okay. So we have the formula, right? VEL di over dt. V is L di over dt. Okay, so that means IE 1 over L with dt, right? We studied at the high school, right? So VE, so that means that I modify a little bit. You have L di, okay, dt, and move here. You can get V dt. Okay, so I check the integration of both sides. Okay, yeah, and this is L. Okay, so if I delete L here, so this one is over L. So the integration of derivative I, you get I equal to 1 over L integration V dt. Yeah. So now we know the voltage. The voltage is here 1 over L. Okay, so this is constant. So I move outside, so you get the square root of V over L. And this is the integration of cosine omega t dt. So the integration of cosine omega t is sine omega t. So divided by omega, because dt, you need to convert dt to become d omega t. You divide it by omega here. So finally you get what? I e square root of 2 times v. Okay, here you get 1 times omega L and then sine omega t. Sine omega t is cosine omega t minus pi over 2. Why? We need to convert sine become cosine. Why? Because the format of the voltage is cosine, right? Is cosine. So you need to make sure the format of the current is cosine, and then you can convert to the complex number. Okay. So now for the complex number, for the voltage is what? E square root of 2v, right? With the phase angle 0, because here u plus 0, right? Now the current, this is cosine. So you get the current E, the square root of 2 current. Now the phase angle how many? Look, minus 90 degree. Okay, so if here is the voltage, okay, you stay here, this is x-axis, right? And then we follow counterclockwise direction, you get positive. You follow clockwise directions, you get negative. So this is minus 90 degrees, so we need to follow counterclockwise. So here is I, right? And the phase angle here is minus 90 degrees. Okay, so that is the reason the current will be lagging. Vietnamese meaning trễ pha. The current is lagging to the voltage 90 degree. Okay, now look, the current lags behind the voltage 90 degree. Okay, now I will draw the waveform. Okay, now look, current cosine voltage minus 90 degree. Okay, so I will draw the waveform. Look, oh sorry, this one is the waveform omega t. I draw the voltage first. Here, 0, 80, 180, 270, 360, minus 90, minus 180, minus 270, and minus 360. Okay, so if omega t is 0, okay, we get big. Okay, negative. Okay, so you get a waveform like this. Yes, the waveform of the voltage like this. Yes, okay, this is voltage. So about current, okay, look, this is minus 90 degrees, so that means right shift with 90 degree. Okay, so the voltage peak here, so now we make right shift 90 degrees. Okay, so the peak of the current will be here, and the value how many? Look here, square root of 2 times v over omega l, right here, magnitude. Okay, so this is 0, 0, 0, big 0, negative big 0, positive big. So you get the waveform like this. Okay, so now see, the peak of the voltage will be located at the y-axis. Now we have minus pi over 2. So the peak of the current will be right shifted 90 degree. Okay, so here, peak. Yeah, so this is the waveform of the current. Okay, yes. So if you see this waveform, this is minus infinite to positive infinite. That means, okay, that means the voltage get big first. Look, okay, you stay here, right? So here we have the polar form. You know, this is x-axis, this is y-axis. You always stay here, right? Right? You stay here. That means you stay here. You stay here. Okay. So if you stay here, you can see the voltage get big first. Okay. And after 90 degree, the current get big. That means if here is the voltage, here is the current. Okay. And the current is lagging to the voltage 90 degree. Okay. Yes. Yes. Okay. So this is the wafer. Yeah. And now we have conclusion. If we have the inductors, the current is lagging to the voltage, or the voltage is before the current. If we have the capacitor, the current is before the voltage. So here, if we have the voltage, okay, so this one is IC, right? This one is IL, and this one is IR. Okay, for resistors, the voltage and current have the same phase. For the capacitor, the current is leading to the voltage 90 degree. For inductors, the current is lagging to the voltage. Okay, that's it. Or if we say here is the current, so here is VR, here is VL, and here is VC. It's up to you. Okay, but normally when we draw the waveforms, sorry, when we draw the vectors, we normally use the voltage. We normally use the voltage as the reference. Okay, as the reference. Okay, and this is IR, IC, IL, but you can use I as the reference. So this is VR, VL, VC. Okay, yeah. So now, and similarly, we can calculate the average values of the power for inductor. Of course, this is zero. It is zero. So we have the conclusion: the net power dissipated when an inductor is subjected to an AC voltage is zero. Okay. So now, this one for your reference. We will discuss this one for another course, electric circuit. Now we don't have free time, so we don't have more time, so we just skip it for your reference. Okay, or you can answer TA. Okay, they will answer to you. Okay, so yeah, for your reference. Yeah, so we finished the application of complex number into very basics electric circuit. Okay, we have three, right? We have resistor. We have resistor. We have the circuit with resistor, the circuit with inductor, and the circuit with capacitors. Okay, and we have some slide here just for your reference. Okay, you can study for yourself, or you can add the TAs. Okay, they will explain to you. Okay, so yeah, maybe we have some questions before we take a break. Any questions? We haven't learned that in the high schools. Can you repeat that? I still don't understand. And what is the difference between XC and ZC? Yes, of course, we have recording today. I hope everything is okay, and maybe today, yeah, they will keep the recording carefully. Okay. Okay. So, oh, you haven't learned the knowledge at the high school. Okay, just let you know some application of complex number into the basic circuits. Okay, TA, please, yeah, and support him when I finish the lecture today. Okay, to give him more explanation about, yeah, about this phase angle between voltage and current for resistive lot, capacitive lot, and inductive lot. Okay, so what is the difference between ZC and LC? Yeah, this is good questions. Okay, I will answer to you. Okay, so now, yeah, we come back. Okay. Okay, we come back. So now we have the comparison. Okay, we have the comparisons. We have the comparisons. Okay, so okay, we have resistive lot. Vietnamese tài trợ. We have capacitive lot. And we have inductive lot. Okay, ideals. Okay, ideal case. Ideal case. So here we have voltage. We have resistor with the value of resistance and the current. Okay, so we say voltage has the same phase, the same direction with the current. Okay, and when we apply law, you get VEI times R. Okay, so that means if here is V, here is I, right? They have the same phase. Okay, so that means I EV over R. Do you agree with me? Yes. Okay, so the same phase, that means if the voltage is 0 degree, the current should be 0 degree. Okay, yeah. So now we apply to this one. So the current is the voltage with 0 degree over R. So R should be 0 degree. Okay, this is 0, this is 0, so you get V over R with 0 degree. Okay, so now for resistance, very easy because the phase angle here is 0. Okay, so I don't want to say R, I say ZR. So ZR is R, right, with the phase angle 0. So this one is ZR. ZR. Okay, so what is Z? Z is impedance. Impedance. Okay, so for more general, impedance is R plus JX. Okay, now we just have R, we don't have X. Okay, this is impedance. Okay, now capacitive lot. Okay, now voltage capacity. This is C. This is the current. Okay, if we apply Ohm law, the unit here should be Ohm, but C, the unit is farad. You know, this is farad. Okay, so we cannot apply Ohm law. Doesn't mean VAI times C. No. Why? Because the unit of capacitors is farad, not Ohm. So we cannot apply Ohm law immediately, right? So we think about, we modify C become XC. And everybody know, right? XC is what? XC at the high school is 1 over omega C. Okay, now this is Ohm. Okay, and XC is 1 over omega E2 by FC. Okay, so now we can apply Ohm law, right? Because we modify C to become XC. So XC, we say reactance. Okay, now we apply Ohm law. So when we apply Ohm law, you can know vector V E vector I times what? Time vector X. Okay, time vector X. Because this is the capacitive load. Okay, because this is the capacitor load. So if here is the voltage, here is the current, right? So that means if the voltage is 0 degree, the current will be how many? We stay here, right? And we follow counterclockwise, you get positive. So the current will be 90 degree. Okay? 90 degree. So that means IEV over vector x. Vector x. Okay? So the voltage EV with 0 degree, okay, we should get XC with minus 90 degree. Why? Because if here is minus, okay, you move to the numerator, you get V over ZC, and this is 90 degree, okay, the same. Look, do you understand? So the XC with minus 90 degree, we say ZC. Okay, now we have ZC E XC with minus 90 degree. That means JXC. Because here is real, this is imaginary, okay, or this is J, okay. So ZC should be here, and you get 90 degree. Okay, sorry, minus, right? Minus. So minus. So okay, so here. Okay, ZC should be here. Okay, ZC should be here. Okay, so that is the reason for capacitives. Okay, ZCE minus JXC, and XC is what? XCE here, 1 over J omega C. Okay, so that means here, okay, you get minus JXCE 1 over omega C. So I get minus J here, 1 over omega. I times J here and I times J here, right? So J and J, you get J squared is minus 1 minus and minus, you get positive. So you get 1 over J omega C. Okay, so sometimes we say ZC is minus J times 1 over omega C, or you say ZC is 1 over J omega C. Okay, so that's the difference between ZC and XC. Okay, now the last case. Now this is voltage, this is current, and now we have inductors, idealized inductors. Okay, this is L, this is voltage, this is current. Okay, so remember this is L, so the unit is Henry. You cannot apply Ohm law, right? Because Ohm law, you need to get Ohm unit. So we modify L becomes XL. Okay, so XL is what you know, right? XL is omega L. This is high school study, right? XL is omega L, or 2 by FL. Okay, now remember that if the voltage, the current will be here. Yeah, we demonstrate before. If we have inductive load, this is voltage, this is current, and this is minus 90 degree. Okay, so that means if we have IEV over vector XL, okay, and V with 0 degree, so this is V, right? V is V with 0 degree, so I now is I with minus 90 degree. If you would like to get a minus, you need to divide this by what? 90. Okay, because this is plus 90, so if we move to numerator, you get V over XL with minus 90 degree. Okay, so now XL with 90 degree, that's a what?
That's a ZL. Okay, so ZL is XL with 90 degrees. That means JXL, right? JXL. Because this is real, this is imaginary or J. So this is vector ZL. Okay, so now this is ZL. This is XL. This is ZC. This is XC. Okay, I hope you enjoy it. Is it clear? Vâng Đức. Okay, so if you have no further questions so far, so we take a break 10 minutes and we will come back what time, so we take a break of 10 minutes. So now we have 10. Now we have 10 55, so we come back 11 and 5. Okay, yeah.